This is the 9th lecture in the first semester Java course presented by Savage River Research. To view all of the currently available lectures, point your browser to savageriverresearch.com and click on Open Courses. These are the topics that will be covered in Lecture 9. But before we begin, let's review the solution to the programming problem assigned at the end of Lecture 8. This is an electron microscopic image of the first U.S. case of COVID-19. The virus itself is stained in blue. This shows the ultrastructural morphology exhibited by coronaviruses. As noted in Lecture 8, the currently reported average diameter of the virus particles is about 125 nanometers, but close measures have shown some troubling variances. Your company, Hurricane Island Research, has a contract to build a software prototype for the CDC that will query the user for the diameter in nanometers of 5 randomly chosen virus particles measured by a technician. The technician will enter those values and your system will output the mean, the variance, and the standard deviation of the 5-sample set. The requirements document calls for an initial message dialog screen, bordered here in red, followed by 5 input dialog screens seeking user input, followed by a message dialog screen outputting the results of your calculations. In the real world, the graphics on all of the screens would be described in something called the requirements document and could be legally enforced by the client through provisions in the contract. This is a typical scenario in the industry. You will seldom, if ever, work in a vacuum. The software you're paid to produce has to comply with the documented requirements of the client. Generally, there are financial penalties attached to any failure to deliver on time and as specified, so you may as well get used to that now. Okay, here's the problem description again, and here's slide 174 from Lecture 8, describing exactly how mean, variance, and standard deviation should be calculated. Armed with that knowledge, a reasonable path to the solution might begin with the declaration of 3 double variables, mean, variance, and standard deviation, and a string variable to hold the user input. The problem domain appears to be entirely linear, simply requiring a succession of screens. And the first one should be a show message dialog screen, and it has to be coded exactly as described in the requirements. Now, take a closer look at the parameter, in particular, the placement of the \n construct and the use of blank spaces to comply with the client's requirements for this screen. Some clients, particularly federal government clients, demand precise compliance with the screenshots defined in the software requirements document. So you should get in the habit of precision. Next, the first input screen, followed by the second, third, fourth, and fifth. Now, note that I declared and initialized each of the 5 diameters on its own single line. I could just as easily have declared all 5 doubles on one line. It's a matter of individual style. All right, now let's look at our first calculation. The mean is simple. Just add the 5 values and divide by 5. Let me magnify this section so we can see the code a little better. Then move on to the variance. To calculate the variance, I have to subtract the mean from each diameter, then square that difference, and I do that for each of the 5 values. That gives me the variance, sigma squared. Now, let me magnify these 2 areas to show the details. This is method power, a method of the math class. You don't need an import statement to access the math class like the string class. It's automatically available. The power method has 2 parameters, and it will return the value of the first argument raised to the power specified by the second argument. In this case, d1 minus the mean squared. And all I have to do to calculate the variance is do that 5 times. Then sum the result of those 5 calculations, then divide by 5. Once I have the variance, I can use another math method, squirt, SQRT, square root, to get the standard deviation. Standard deviation is simply the square root of the variance. The math methods do all the heavy lifting. So now just output the results. Okay, here in bold blue is what we've covered in this lecture, starting with what we will cover rather in this lecture, starting with the if statement. The if statement decides whether a section of code executes or not. It uses a Boolean to decide whether the statement executes. If the Boolean expression is true, execute the statement. Here, cold outside is a variable of type Boolean, initialized to true. If the if statement evaluates to true, and obviously it does, since cold outside has been set to true, a show message dialog box will appear displaying the statement, wear a coat. Then execution should move to the next statement after the if construct. But if we had initialized cold outside to false, then the if statement would not execute, and execution would simply skip directly to the next statement after the if construct. If statements can be modeled as a flowchart. Since cold outside is initialized to true, the if evaluates to true, executing the show message dialog method, which displays wear a coat. But now, let's change that true to false. Then the Boolean expression, if cold outside, evaluates to false. So skip the statement attached to that if and execute the next statement, whatever that is. But it's important to note that we're not just limited to one statement here. Using a pair of braces, we could execute several lines of code when cold outside is true, or skip all of them when cold outside is false. Now, remember, this line, the next statement, executes no matter what the value of cold outside is, true or false, doesn't matter. The next statement executes. And note that each of these executable statements end in a semicolon, but a set of braces never ends in a semicolon. Now let's consider relational operators. In practice, the Boolean expression used by the if statement typically employs relational operators. There are 6 of them. And here they are. First, the right pointing arrowhead operator is greater than. Next, the left pointing arrowhead operator is less than. Then the right pointing arrowhead operator concatenated with the equal sign is greater than or equal to. The left pointing operator concatenated with the equal sign is less than or equal to. A concatenated set of equal signs is equal to. And the exclamation mark concatenated with the equal sign is not equal to. A Boolean expression is any variable or calculation that results in a true or false condition. This one asks the question, is x greater than y? Where x and y are typically numeric values. This asks the question, is x less than y? And here, is x greater than or equal to y? Is x less than or equal to y? Is x equal to y? Is x not equal to y? Now, let's take a look at these in the context of an if statement. If x is greater than y, print the statement. If that's not true, don't execute the print line. But here, execute if and only if x and y are equal. Now consider this one. If x equals y, nothing is printed. If they are not equal, these 3 statements are printed. But note, the fact that I then set x equal to y on this line has no impact on this Boolean test. We've already passed that line. An if statement that's composed of a Boolean test and a single executable like this can span more than one line or be written on a single line. These 2 statements are functionally equivalent. But the general rule of thumb is that the conditionally executed statement should be on the line after the if condition, and that the conditionally executed statement should be indented 1 level from the if condition. That's just for readability. If an if statement does not have the block curly braces, like the curly braces we looked at a few slides back, it is ended by the first semicolon encountered after the if condition. But as we just saw, a set of conditionally executed statements can be grouped into a block by using curly braces to enclose them. And, as we just saw, if curly braces are used to group conditionally executed statements, the if statement is ended by the closing curly brace. Note that no semicolon follows that brace. But remember that when the curly braces are not used, then only the next statement after the if condition will be executed conditionally. These next 2 statements will be unconditionally, sequentially executed no matter what the result of the if statement. Makes no difference whether the expression is true or false. These 2 get executed. Now, let me throw some braces into the mix. And when I do that, these 2 statements will be conditionally executed. That is to say, they will be executed if and only if the expression is true. If the expression is false, they will not be executed, but the next statement, this statement, will execute no matter what happened above. The fact that it is indented is irrelevant. Now, let's talk a little about flags. A flag is a Boolean variable that monitors some condition in a program. When the condition is true, the flag is set to true. Then the flag can be tested to see if the condition has changed. So here, if average is greater than 95, the Boolean high score is set to true. At some point down the road, the flag, high score, can be tested. And if it's true, the congratulatory note is output. Now, so far, we've used relational operators on numerics. But variables of the primitive data type char can also be tested with relational operators. Just keep in mind that relational operators are binary operators. They require left and right operands of the same data type. If you try to write one without a left and right operand, you'll get a compile time error. So if I have literal chars or variables of data type char on both sides of a relational operator, the specified Boolean test will be performed. But exactly how does this work? Well, remember that characters are stored in memory using the Unicode character format. Unicode characters are stored as 16-bit numbers. But the characters are also ordinal, meaning that there is an order in the Unicode character set. And since characters are ordinal, they can be compared to each other. If we declare C to be a variable of type char and initialize it to the character capital A, then we can use the relational operator less than to compare the variable C to the char literal Z. If the contents of the char variable C, whose value is now the character A, if those are less than the character literal Z, the statement will be output. But how can you tell what's going to happen? How do you know whether the value of the variable C is less than the literal Z? Well, remember ASCII from lecture 2.2? The capital letters are stored as binary values, sequence of zeros and ones. But those binary values can be directly translated into their equivalent decimal values. And these two values can be compared. That's what CPUs do for a living. So here we can easily determine that the contents of the char variable C, which is the character A, whose numeric value is 65, is in fact less than the numeric value of the literal char Z, which is 90. Therefore, the Boolean test returns true, and the message A is less than Z will be output to the console. Note also that the lowercase characters follow a similar pattern. All of the lowercase characters are numerically greater than the largest of the uppercase characters, and that lowercase characters increase as you move from lowercase a through lowercase z. Okay, now let's look at the if-else statement. The if-else statement adds the ability to conditionally execute code when the if condition is false. One of these two statements will execute depending on the value of cold outside. If cold outside is true, the computer's advice is to wear a coat. If cold outside is false, the computer's advice is to wear shorts. And this is how it looks modeled as a flowchart. But if statements can also be nested. If an if statement appears inside another if statement, single or block, it is called a nested if statement. The nested if is tested only if the outer if statement results in a true condition. When modeled as a flowchart, it looks like this. So let's walk through it. Here's the code. Note that the Booleans cold outside and snowing are set to false. And since cold outside is false, this exterior statement does not execute. So there's no way the nested if can be tested. And the execution path goes directly to the else, and the output is wear shorts. Now, suppose I change the value of the Boolean snowing from false to true. What happens then? Take a minute. Think it over. What will be output? Pause the recording. Write your answer down. It's the only way to find out whether or not you understand what I've been saying. The outcome is the same. As long as the Boolean expression for the external if evaluates to false, the nested if is never tested. This condition is not tested if this condition is false. Okay, let's change the Booleans again. We'll make cold outside true and snowing false. What happens then? Take another minute. Think it over. What will be the output? Pause the lecture. Write your answer down. If cold outside is true, we're going to test the nested if. There's no way around that. If cold outside is true, the nested if has to be tested. And when we evaluate snowing, it will be false, which routes execution to the else of the nested if else. Okay, we have two Booleans, so there are 4 possible combinations. We looked at 3, so the only remaining possibility is true, true. What happens with true, true? Take another minute. Think it over. What will be output? The output is wear a parka. Okay, let's talk about trying to sort these constructs with curly braces. Curly brace use is not required if there is only one statement to be conditionally executed. However, sometimes curly braces can help make the program more readable, and proper indentation makes it much easier to match up else statements with their corresponding if statement. In general, the more complex your if and if-else statements become, the greater the need for braces and indentation to improve readability. And that will become even more important as the problem domains you encounter become more complex, requiring ever more complex nesting. The third type of if statement we're going to look at, the if-else-if statement, makes certain types of nested decision logic simpler to write. But care must be used since else statements match up with the immediately preceding unmatched if statement. Now, let's take a look at what that actually means in code. Everything in red is a reserved word. The reserved words if and else can only be used exactly as Java requires. If expression 1 is true, all of the statements enclosed in the braces below it will be executed sequentially, and the rest of the structure, everything below it, will be skipped over, and execution will resume on the first line of code outside of the if-else-if structure. If expression 1 is false, execution drops to the else-if governed by expression 2. If expression 2 is true, all of the statements enclosed in the braces below it will be executed sequentially, and the rest of the structure, everything below it, will be skipped over, and execution will resume on the first line of code outside of the if-else-if structure. If expressions 1 and 2 are both false, the statements in the braces below expression 1 and 2 are not executed, and execution skips to the next else-if. Now, note that there can be as many else-ifs as your problem domain requires. Each one will be evaluated in sequence. If one is found to be true, the statements in the braces below it will be executed. Everything that remains will be skipped over, and execution will resume on the first statement below the entire if-else-if structure. But if none of the prior expressions evaluates to true, if they are all false, execution falls to the else. All of the statements enclosed in the braces below the else will be executed sequentially, and execution will resume on the first statement below the if-else-if structure. Now, one final point. It's perfectly acceptable to write a series of else-ifs with no final else. If any of the expressions are true, statements in the braces below the first expression that is true are executed, and execution will resume on the first statement below the entire if-else-if structure. If none of the expressions are true, this code fragment, the entire if-else-if structure, has no output. Okay, now let's take a look at logical operators. Java provides two binary logical operators, the double ampersands and double vertical bars that are used to combine Boolean expressions, and one unary logical operator that can be used to reverse the truth of a Boolean expression. So, will this output A, B, C, or nothing? Well, A is greater than B, and B is greater than C. So you'll definitely get a message dialog showing ABC. How about now? This expression is false. A is not less than B, but this one is true. and they're joined by a logical OR. And it's only necessary for one of these two expressions to be true. If so, that makes this entire expression true. So this one prints out ABC also. Okay, how about this? Take a minute, pause your recording, work your way through this, and write your answer down. Will the message ABC be displayed? Or will nothing be displayed? A is not less than B. So this fragment of the expression is false. But the not of a false is true. So this fragment of the expression is true. And since B is greater than C, this fragment of the expression is also true. And the logical AND of a true and a true is also true. So this also prints ABC. Okay, let's work another programming problem. This is program 8. It was assigned in lecture 8, and we just worked through the solution at the beginning of this lecture. But now your client has submitted a change order. The client wants you to modify the code so that in addition to calculating and displaying the mean, the variance, the standard deviation, it also reports the maximum and the minimum diameter of the 5 COVID particles entered by the user. Okay, starting from here, what changes do you have to make to get the output shown in the red border? What do you need to do to make program 8 perform exactly like this? And remember, the 5 inputs can be any positive set of integers. Now, obviously, you're just listening to YouTube video, and you can just let it continue to play because the solution starts in a few seconds. But if you're serious about developing a professional level of competence in Java, you have to work these programming problems. Excuse me. That means that you pause here, think through the problem, sketch a possible solution, code it, then test it. If it doesn't work, restart this lecture. The problem's designed to test your understanding of the material I just discussed. That has been the pattern so far, and that testing will continue going forward. But I'll be introducing increasingly complex topics in Java and increasingly complex problems to test your mastery of those topics. So pause here and work through this problem on your own using Eclipse. Okay, the first 14 lines of what I'm now calling Program 9 can stay just as they were in Program 8. That'll get us started. But now we have to determine the maximum and minimum diameters of the 5 inputs, and there are a variety of ways to do that. But one of the most efficient in terms of required lines of code would be to declare min and max as double variables and set them both equal to the first input, d_1. Once I have that, then for each succeeding input, I can determine whether or not this new input is less than the current value of min. If it is, I'll set min to this new lower value. If not, min will retain the value of d1. And then I'll do the same thing for max. Now all I have to do is repeat this same test for each succeeding value. Then, when these last two if statements have been executed, min will be 110 and max will be 140 if the user's inputs were the ones shown in the yellow box. Now all I have to do is modify the output statement to report the results. Okay, now let's revisit order of precedence and incorporate the logical operators we just looked at. Incorporate those into the operators we examined previously. The exclamation mark, used as a unary operator representing the logical not, now has the highest order of precedence among all the operators, followed by multiplication, division, and modulus, all equivalent, then addition and subtraction, both the same level. Then less than, greater than, less than or equal to, greater than or equal to, all at that level. And moving down lower, the Boolean test of equal to and not equal to. Down one more level of precedence, the logical and down one more, the logical or. And finally, the 6 assignment and combined assignment operators. Now, again, in any complex expression, I highly recommend the use of parentheses to make your intentions explicit and easy to read. I never try to evaluate complex expressions based solely on my competence with order of precedence. Now, let's take another look at how far we've come with reserved words. A few lectures back, we started with the primitive data types, all of which are defined by reserved words. 6 are numeric. Of the 6 numerics, 4 are integers, and 2 are floating point. These 8 are the special purpose basics we've encountered so far. We've been using public, class, static, and void from the beginning. Import and null appeared recently. We used new to create an object of the scanner class, and final to declare a constant. In this lecture, I discussed Boolean expressions that evaluate to exactly one of 2 words, true or false, and the keywords if and else, which will be used to build decision mechanisms. Now, it may be time to put some of this to use. This is program 10. Pause the recording, read through it, and read through it until you understand the problem domain. Here's the sequence the client requires. Enter X. The user enters some integer value. You're guaranteed that the user will only enter positive integers in the range for data type int. In later lectures, we'll discuss defensive programming to protect your code from idiotic inputs. But right now, we're going to assume that users know what they're doing and follow the rules. When the user clicks OK, the enter screen for Y is displayed. When the user enters some integer and hits OK, the enter Z screen is displayed. When the user enters some integer and hits OK, the message screen is displayed. And since both X and Z are 560, but Y is 72, Your message is x equals z, but y does not. Now, after you've coded program 10, test it with 5 sets of integers that trigger each of the 5 possibilities. The topics highlighted in blue were covered in this lecture, and these topics will be covered in the next lecture, Lecture 10.